In this video, we will use an Excel model to demonstrate the use of the resampling or Monte Carlo analysis. And we will use this method to calculate best estimate p-values for the two-sample t-test and the Mann-Whitney test. And we will start by using 4 experimental pH measurements from each of 2 rivers A and B. And we wish to test for a difference in the mean and median values of these 2 rivers. And starting with the t-test, we will calculate a pooled standard deviation with the calculation given in the formula bar by taking the variance of each of the samples, multiplying each variance by the sample size minus 1, which is 4 minus 1, which is 3, adding the 2 variances together, then dividing by 6, the sum of the 2 3's, to get an average variance, and then taking the square root, giving a pooled standard deviation of 0.070. We can now use this to calculate the T statistic, which is calculated as the difference between the 2 mean values of the rivers, calculated by taking the average of the data for both rivers, and then divided by the pooled standard deviation in F11, which is multiplied by the square root of 1 over the sample sizes of both samples, giving a T statistic of 2.42. We can record these experimental measurements for later reference with a pooled value 0.0702, the T statistic of 2.42, and if we perform the Mann-Whitney analysis for a difference in the mean values, the relevant statistic is the upper W value, which is 25 for this experimental data. So now the problem becomes more general than our specific pH values. We are now looking first of all for the t-test for the probability in the null hypothesis of any data samples with a 0 difference in mean values of recording by chance a T statistic of greater than 2.42. And then when we move to the Mann-Whitney test, we'll be looking for any 2 data samples with a 0 difference in median values recording a W statistic of equal to 25 or greater. To carry out this analysis, we do not need to use samples with a specific pH value of 7, and we will generate new samples randomly, selecting data values from a normal distribution which has a 0 mean value, but we will keep the pooled standard deviation of 0.702 for continuity, although we could use any other specific pooled value, and we will generate these random values by using the norm inverse function and entering rand to generate a random value between 0 and 1 with the mean value as 0 and the standard deviation, and we're using our pooled standard deviation. And in order to maintain reference specifically to D2, when we copy this formula into other cells, we will lock the reference for both column and row. This has randomly selected a value from a normal distribution, and every time we have a new data entry, or indeed every time we press the function F9 key, it generates a new value. We will now copy this formula for generating random values down to generate 4 values for each of A and B, and our previous formula for pooled standard deviation now calculates the pooled standard deviation of this randomly generated pair of sample values and calculates the T value. This data satisfies the null hypothesis in that there is no difference between the mean values from which the data was derived and any observed T statistic other than 0 occurs due to random variations. And if we repeat the random generation, we get new T values. And for the purposes of our analysis, we wish to calculate the probability that our null hypothesis data will randomly generate a T statistic greater than 2.42. To do this, we will enter an if function into this comparison row to test whether the randomly generated T statistic has an absolute value greater than our test value of 2.42. And the if test takes the value in F12, the randomly generated T value, and takes the absolute value, because we are using a two-tailed test and we could have a type 1 error going in either direction for positive or minus values of the T statistic, and we're testing whether this value is greater than the test value in B4. If it is, it records a 1 in the comparison row, which will indicate a type 1 error, or a 0 otherwise. And this generated value of 0.13 is less than 2.42, so there is no error, we record a 0. If, however, we have a randomly generated T statistic which has got an absolute value greater than 2.42, it records a 1 to indicate a type 1 error. We need to repeat this very many times to assess the overall probability of recording a 1. And to do this, we will copy this whole calculation to a total of 10,000 columns within the spreadsheet, giving us now 10,000 calculations, some of which will record a 1 in the comparison row. For example, we can see that sample 9974 has recorded a type 1 error. If we return to the beginning, we can now calculate the proportion of these sample calculations that have recorded a type 1 error just by taking the sum of the values from F13 all the way through to NTU13, which will record the total number of ones, and then dividing that by the total number of tests, which is 10,000, giving us a proportion of type 1 errors of 0.0501. Clearly, when we repeat the random generation, we will get a new overall proportion. This is our best estimate p-value associated with the T statistic of 2.42. But we need to get some estimate of the uncertainty in this, so we will use the standard formula for calculating the uncertainty in a proportion, which is the square root of the proportion times 1 minus the proportion divided by the number of measurements, in this case 10,000. This gives us a standard deviation in this proportion of 0.023. And to calculate the confidence interval, we can multiply this standard deviation by 1.96 to get the minimum value for the confidence interval equal to the mean, and this will then be minus 1.96 times the standard deviation. And we can calculate the upper level of the confidence interval by taking the proportion, and in this case we'll add 1.96 times the standard deviation, so that now we get a best estimate confidence interval for the p-value associated with our T statistic of 2.42, which is for this set of randomly generated values from 0.045 to 0.053. In the next part of this analysis, we perform the Mann-Whitney test for a difference in median values. We will use the data for the two samples generated in rows 2 to 9 and calculate the ranks of each of these data values in rows 15 to 22. So in row F15, we enter the rank function, which calculates the rank of the value F2 out of all of the values for both samples from F2 to F9. So for this set of data, 0.079 has the rank of 2 within the 8 values. And we can copy this calculation down to calculate the ranks of all the other data values. We now calculate the sums of ranks in each sample. For sample A, this will be the sum of the 4 values. And similarly for sample B, again the sum of the 4 values, giving us the two sums, WA and WB. Repeating the procedure for the t-test, the type 1 error will occur if our null hypothesis data generates a W value, either WA or WB, for the two-tailed analysis, which is greater than or equal to our experimental W statistic of 25. And to test whether this occurs, again we will enter an if function, and this if function tests first of all whether WA is greater than or equal to the value in B17, or whether WB, which is in F25, is greater than or equal to the B17 value. If either of those is true, it records a type 1 error with a 1, otherwise the 0. So again, most of the randomly selected values will not give a type 1 error and will give a 0, but occasionally, repeating the random generation, we will see that we do get a type 1 error for this test for a difference between the two medians, and in this case we also see we're also getting a type 1 error for the t-test as well. To calculate the proportions of type 1 errors, we will again copy this calculation to a total of 10,000 columns. Giving us our 10,000 calculations, and we see that the calculation here has recorded a type 1 error. So returning to the initial calculations, we can calculate the proportion of type 1 errors by using the same formula that we use for the t-test, just by copying these formulas here for our Mann-Whitney test. And this tells us that for this particular set of sampled data, the probability of obtaining either a WA or a WB value greater than or equal to 25 is 0.0602, which is our best estimate value associated with the W statistic. We again calculate the standard deviation in this proportion. This gives us a confidence interval for the p-value. So overall, from the initial experimental data, which gave a T statistic of 2.42 and a W statistic of 25, we get best estimates from 10,000 samples of the P range for the t-test for a difference in mean values of 0.049 to 0.058, and the best estimate for the p-value for the Mann-Whitney test of 0.056 to 0.065.